Welcome to AP Podcast 14.5. This is on weak acids. And so look at this. Ka will be small. Yeah, duh, we know that already, right? We know that this is an equilibrium, and we know that weak acids are weak because they don't break up completely. In fact, they don't break up very well at all. And so that's one of the facts that we've got to keep in the back of our mind because it's going to really change the way we do these problems. So like always, if you look at these other bullets here, list the major species. Okay, that's what we do. Choose the species that could produce H plus and write the reaction. Yeah, we do that. Based on the K values, decide the dominant equilibrium. All right, that sounds good. And then write the equilibrium expression and list initial concentrations. So that's all stuff that we've been doing since we've been doing equilibrium problems way back in chapter 13. But we're going to have to treat them a little differently because the fact it's a weak acid. So let's look at these. All right. So here are our points for doing equilibrium problems with weak acids, and you'll notice that this stuff is super familiar to you. Right? Look at that. Define the change in equilibrium as x. Okay, we did that when we were doing equilibrium problems. Write the concentrations in terms of x. So remember when we were going like 1.0 minus x for concentrations in the ice table before? And then same thing when we're doing whatever product we have. Substitute equilibrium concentrations into the equilibrium expression and then solve x the easy way. Now, what's the easy way? Well, if you remember, let's say, for example, I write out an equation here, and I've got H plus A minus, and I've got HA, right? Now, on the bottom, it would be something like 1.0 minus x, right? Now, the easy way, if you recall, is us just ignoring that bottom x value, right? Because we know that in this equilibrium, right here, oops, A minus, I'm sorry about the writing, that is pretty bad even for me. We know that in this equilibrium that the amount of H that's actually going to go to the product side is going to be super small. So remember, we just ignore that, and that makes the mathematically the problem very easily done. Okay, and then of course at the end we should check just to make sure that the 5% rule holds. But again, like I told you when we were doing equilibrium problems, in AP they always hold. And if not, we would do a quadratic equation, and they don't do quadratic equations in AP, and so we don't really have to worry about that. Not to say we won't do a quadratic in class for funds, all right? And then once you've got the H concentration, you can find the pH, all right? So let's try one. Here we go. I've got a problem, and actually there's two bullets, so I'm going to do the first one. Calculate the pH of a 1.0 molar hypochlorous acid with a Ka of 3.5 times 10 to the minus 8th. Okay, so what are the major species here? Well, besides this thing, what's the other thing floating around? As you guys know, there's water floating around. And who's going to override this equilibrium? Of course, it's going to be the hypochlorous acid. So what I would normally do is I would write out the Ka. Ka equals 3.5 times 10 to the negative 8th. And that equals H plus OCl minus over HOCl. Okay, so there's my equilibrium expression. And then if I plug in the values I have for here, I know that above I'm going to have x for both, right? So I'm just going to write x squared. Okay, and then on the bottom, the amount there is, what is the value? Oh, here we go. We've got 0.1 molar. We've got 0.100 molar minus x, right? And I didn't set up a big ice chart, and if that's something you need to see, just remind me in class and we'll do it. But again, we're going to make this the easy way, so we're going to ignore this x, and then we're just going to solve for the concentration of H plus here, and when I do that, I get a value of 2.7 times 10 to the minus 2, okay, molar. So that's my H plus concentration, right? Now, again, checking for the 5% rule is basically, look at this number, that's this number right here, 2.7. Is that less than 5% of 0.100? Absolutely. Matter of fact, if you wanted to do the math, it would be 2.7% dissociated. So by doing that, we're okay. Now, if I take that number, the 2.7 times 10 to the minus second, and I put that in my calculator, I get a pH of 1.57. Okay, so there it is, an equilibrium problem involving a weak acid. Okay, so now that you've had time to look at that one, pause the video and try to find the POH, the OH, and the H plus concentration for this problem. I will write it out and you'll see if you get the same thing I get. Alright, are these the answers that you got? You can see that I set up my equilibrium here, and then I get an H plus concentration of 0.006, and then I get the OH concentration by dividing into kW of 1.67 times 10 to the minus 12, and then I took the negative log of that and I get a POH of 11.8. So hopefully that's what you got. If not, again, we'll talk about it in class tomorrow. Alright, so let's look on the next thing. Now, what happens if you mix a couple weak acids together? Well, what's nice about these problems is typically they're going to be two acids that have a vastly different Ka. And because of that, what you can do is you can take the Ka of the stronger one and just treat it as a single acid problem. And what I mean by that is, let's look at this problem right here. Calculate the pH of this. Now look at the Ka for this thing. 1 times 10, or 6.2 times 10 to the minus 10th, and 4 times 10 to the minus 4th. Now, if you imagine the difference between to the minus 10th and the minus 4th being 6 times, or a million times, I guess is the way I should say it, we know that the fact that nitric acid, or nitrous acid, is going to donate almost all of the H+, whereas the HCN donated by this guy right here, with this Ka, is going to be virtually non-existent. So what you would do is you would solve that problem normally just using the HNO2, and if you do, you'll get this answer that I have right here. And so if you feel like you want to practice it, try it out and make sure that you get a pH of 1.35. But let's look at this other problem, because this other problem is rather interesting. And you guys know how AP likes to throw us some interesting problems. What's the concentration of the Cn minus ion in the solution at equilibrium? Now, I just told you that we're not even going to worry about this this acid right here in the 1 molar hydrocyanic acid, but we are being asked about what's the concentration of this Cn. And so we've got to do a little work to figure that out. So let's look at the next slide, and I'll show you how this works. All right, well, the first thing I'm going to do to approach this problem is I'm going to write out my equilibrium expression. Okay, so I've got my Ka equals, and then we've got 6.2 times 10 to the negative 10th, right? And that's going to equal this. It's going to equal H plus Cn minus all over the concentration of HCN. Alright, so now I've got this written out, and remember, we're trying to find this concentration. Now, you might normally say, well, duh, it's the same as whatever the H concentration was in the problem before. But remember, the H concentration was from the nitrous acid. Alright, and so what we've got to do is plug in the numbers that we know. Well, we know the H plus concentration being 0.045. Now, if you're going, well, where did you get that number? Well, if you would have done the previous problem and you would have solved this for HNO3 to get this pH right here, okay, to get that pH right there, you would have found it to be 0.045. So sorry if I confused you there. But anyway, so I've got that number. I still don't know the concentration of my Cn. That's my X value, right? And then what was the molarity for my HCN to start with? It was 1 molar. Okay. So the tricky part is, of course, realizing that all of the H right here is from the HNO2. And that might not be something that's obvious to you. So that's what makes this problem a little tougher. But now that we've got it set up and you guys are all amazing at math, when you work that out, you get a value of, for Cn to be 1.4 times 10 to the negative 8th molar. And so it's a rather small concentration. But hopefully that makes sense, because look at the Ka of this thing. Look how small it's going to dissociate anyways. Right? So we would expect a number to be very small. But I'll tell you, if people aren't paying attention on a test or something like that, they'll go ahead and put the wrong H plus concentration in there and get this problem wrong every time. All right? So there's that. We'll talk about this later.